This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to This Explainer. Today, we are going on a totally mind-bending journey that actually bridges the gap between high-level fluid mechanics and ancient Iron Age history. We're diving into the rheology of time and matter. Now, if you're not familiar, rheology is the study of how materials flow and deform. And today, we're going to see how the very definitions of what we call a solid or a liquid are actually kind of just illusions. They're illusions created by our own human perception of time.
So here's the big question. Can solid mountains flow like liquid water? I mean, when you look at a massive mountain range, it feels like the ultimate symbol of static, unyielding permanence, right? But what if literally everything we consider solid is actually just an incredibly slow-moving liquid? What if the only reason you don't see the rocks splashing and pooling around you is simply because you aren't living long enough to watch it happen? Stick with me, because by the end of this explainer, you are absolutely going to look at the ground beneath your feet in a completely different way.
Okay, let's map out our roadmap for today. We'll be covering 1. The foundations of viscoelasticity. 2. Time and temperature superposition. 3. The biblical prophetess Deborah. 4. Deborah versus Weissenberg numbers. And finally, 5. Do mountains really flow? Let's dive right in.
Section 1. The foundations of viscoelasticity.
To figure out how mountains could possibly flow, we first have to tackle the core physics of linear viscoelasticity. This is a specific class of material behavior where the mechanical response actually displays both viscous, fluid-like characteristics, so think of honey pouring, and elastic, solid-like characteristics, like a rubber band snapping back. When you apply infinitesimal strains, these materials can act like both fluids and solids, depending entirely on the load you put on them. Basically, it means that the relationship between stress and strain is completely time-dependent.
And you know, that time dependency brings us to this truly brilliant axiom in physics, the Boltzmann superposition principle. This principle states that a material's response to a complex loading history is just the linear summation of its responses to every individual stress or strain increment from its past. It's almost like the material has a fading memory. Every single time you apply a load, it leaves this little memory in the material that just slowly fades over time. Mathematically speaking, this is expressed using Stieltjes-type hereditary integrals. You've got a relaxation representation where the strain history yields the stress, and a creep representation where the stress history yields the strain.
Section 2. Time and temperature superposition. So time is obviously crucial here, but it turns out temperature acts kind of like a remote control for a material's internal clock. We call this the time-temperature superposition principle. If you look at a typical master curve, you'll see two extremes. On one side, you have the glassy region. This happens at very short reduced times or really low temperatures. Here, the polymer chain segments are totally locked in place, giving you a rigid, brittle solid with a high modulus. But then on the complete opposite extreme, we have the terminal flow region. This happens at very long times or high temperatures. In this state, the physical entanglements untangle, macromolecules undergo long-range translational motion, and the whole thing behaves like a viscous melt. Now, the math that maps this shift in time and temperature is described by the Williams-Landau-Ferry, or WLF equation. And honestly, this equation reveals something pretty incredible about free volume theory. When you fit the WLF equation to experimental data for amorphous polymers, it shows this nearly universal fractional free volume of just 2.5% right at the material's glass transition temperature. It doesn't matter if you're looking at synthetic rubber or specific plastics, right at that exact transition point from glass to rubber, about 2.5% of its total volume is literally just empty space that allows for molecular movement. Pretty wild, right?
Section 3. The biblical prophetess Deborah.
Okay, we're making a pretty massive but brilliant pivot right now from polymer physics to Iron Age history, because we need to find the namesake for this entire scientific phenomenon. Deborah was the fourth judge of pre-monarchic Israel, and she's actually the only female judge mentioned in the Hebrew Bible. During a time of intense political fragmentation, modern archaeological reconstruction places her era around 1200 to 1125 BCE, right in that transition from the Late Bronze Age to Iron Age 1. This time frame includes the 20-year oppression by the Canaanite king Jabin and his general Sisera, which was followed by 40 years of peace. Now, there is also the traditional rabbinic timeline under Seder Olam Rabbah, which places her 40-year tenure a bit later, from 1107 to 1067 BCE. Historically, she was famous for holding court under a date palm tree to ensure absolute impartiality and openness. But her major contribution was actually formulating the military strategy that defeated Sisera's army of 900 iron chariots. To commemorate that massive victory, she co-composed the Song of Deborah, which is one of the oldest surviving compositions in the Hebrew Bible. And here is the absolutely pivotal verse for us, Judges 5:5. The mountains flowed before Yahweh, this Sinai before Yahweh, the God of Israel. This ancient text paints a really striking picture of a volcanic and metallurgical theophany, where the very rocks themselves melt like slag in a smelting furnace. The key to this entire connection is the ancient Hebrew root word nuzzle. Some later Western translations try to translate this as the mountains quaking or trembling, treating it just like a standard earthquake. But modern philological scholarship confirms nuzzle literally means to flow, run, stream, trickle, or liquefy. The poetic imagery specifically, and very intentionally, represents massive, static mountains becoming a fluid liquid. Section 4. Deborah versus Weissenberg numbers.
So what does this ancient poetry have to do with modern physics? Well, the crucial point is how this connects directly back to non-Newton fluid mechanics. Back in 1964, Marcus Reiner, who was a total pioneer of modern rheology, proposed a dimensionless parameter which he named the Deborah number. Drawing on the prophetess Deborah's ancient observation that mountains flow before the Lord, Reiner defined the Deborah number, or D, as the ratio of a material's characteristic relaxation time to the characteristic time of observation. To put it simply, it's just the time it takes a material to physically relax its internal stresses divided by the amount of time you spend watching it.
Now, it's actually really common in science to confuse the Deborah number with a Weissenberg number, but they are entirely different beasts. The Deborah number focuses on flow unsteadiness. It's a ratio of timescales. The Weissenberg number, on the other hand, focuses on flow nonlinearity and is a ratio of physical forces, specifically elastic normal forces to viscous shear forces. The absolute easiest way to remember the difference is this. In perfectly steady, constant flows, the Deborah number is strictly 0. But the Weissenberg number remains greater than 0 because it's tracking molecular orientation, not time-based memory. There is, however, one very specific exception to that rule. These two numbers only coincide mathematically under very precise geometric conditions. A great example is lid-driven cavity flow. If you have a perfectly square cavity driven by a sliding lid, which is governed by a single characteristic length and velocity scale, the process time and deformation rate scale in such a way that the formulas for the Deborah and Weissenberg numbers actually yield the exact same value. But remember, in almost all practical applications, they measure very different physical realities. Section 5. Do mountains really flow? Okay, we can finally bring the physical math and the biblical poetry together to answer that big opening question. When you compare the calculated Deborah numbers of different systems, the results are honestly fascinating. Let's look at Silly Putty. It has a relaxation time of 1 second. If you bounce it, your observation time is about 0.1 seconds. Do the math and the Deborah number is 10. Because that's greater than 1, it acts like an elastic solid and bounces. But if you just leave it sitting on a table for 100 seconds, the Deborah number drops to 0.01, and it flows into a puddle exactly like a viscous fluid. Well, the exact same rule applies to the Earth's mantle. If it's watched for an 80-year human lifespan, the Deborah number is high, so it acts like a rigid solid. But watched for 1,000,000 years, the Deborah number approaches 0, and that solid rock flows just like a fluid. And this whole concept of observation time brilliantly illustrates how we can use the Deborah number to bust a really massive urban myth. Have you ever heard that medieval cathedral glass is thicker at the bottom because the glass has slowly been flowing under gravity over the centuries? Yeah,
It's entirely false. The structural relaxation time of soda-lime silica window glass is roughly 10 to the 23rd power years. That is far longer than the universe has even existed. Divide that by a mere 1,000-year observation time, and your Deborah number is absolutely astronomical. There is literally no flow occurring. The uneven thickness is simply an artifact of how they spun crown glass during medieval manufacturing, and the masons smartly just put the heavy, thick edge at the bottom.
But rocks? Rocks are different. By using the Oldroyd B constitutive model for viscoelastic flow, geologists can actually calculate the structural relaxation time of the Earth's upper mantle rock. Because of the immense temperatures and pressures down there, the relaxation time of deep rock is calculated to be just 1,056.27 years. That right there is its internal clock. So think about what that means for human observation. In an 80-year lifespan, we're watching a material that takes over 1,000 years to relax. The Deborah number comes out to 13.2. Therefore, to us, mountains appear as rigid, entirely static solids. But in a geological process, like plate tectonics, the observation time is 1,000,000 years. The Deborah number drops all the way down to a minuscule 0.001. Over that time frame, the mountains literally flow under gravity. They creep and move, physically driving continental drift. Which brings us perfectly to Marcus Reiner's profound realization when he first named this principle after the prophetess Deborah. Reiner wrote, "The time of observation of God is infinite. For a Deborah number of 0, all materials, including the mountains of Sinai, are in a state of flow." It is such a stunning realization. The definitions of solid and liquid aren't these absolute fixed properties of matter. They're just relative phenomena, defined entirely by the lifespan of the observer. To a divine observer with infinite time, the Deborah number of the universe is 0, and every single mountain is constantly flowing. It really makes you wonder, doesn't it? What other absolute facts of our reality are simply illusions, born purely from our incredibly brief moment in time?
Like what you share.